Hey, Block 1 folks. Here's something that we're a little bit behind Block 2, or sorry, Block 4, so I wanted to try to get to this before I see you tomorrow. Yeah, what we're looking at is a typical graph that I guess summarizes, or I don't know, yeah, it sort of summarizes the stuff we've seen from photoelectric effect, right? So if you don't know, when I say photoelectric effect, if you don't know what I'm talking about, I recommend you go back and have a look at what photoelectric effect is. Now, this is always a graph of what we call Ke max in joules versus frequency in hertz. Okay. Uh, Now, what the Ke max is of is, well, I'm going to put that down here. Ke max. And that's, well, maximum kinetic energy of electrons ejected from metal. Again, if that sounds like Greek to you, you have to go back and look at, what photoelectric effect is. Okay? F refers to frequency of incident photons. If you don't know what a photon is, go back to the notes from last week. There'll be other stuff we put in here. Now, what you might remember is that a photon's frequency really dictates its energy, or is proportional to its energy, all right, via that formula E equals HF. And so what we're saying here is, photons have a certain energy based on their frequency, and, well, that photon energy can control how much energy the electrons have that are ejected from the metal, which hopefully makes sense. And you would think, hopefully this makes sense, the more energy these photons have, the more energy the electrons that are ejected from the metal can have. So, that sort of suggests a relationship that looks something like this. Ke max, well, I'm going to say is proportional to HF. And you remember that HF, of course, is just E of a photon, energy of a photon. Okay? But the deal is this. It certainly takes a certain amount of energy just to get an electron out of the metal, right? Just to rip it out of there. All right? So how that shows up is this thing here called phi. And phi is called the work function of the metal. Right? It's characteristic to each different metal. Each metal has its own phi. And this really refers to energy required simply to remove an electron from the metal. Okay? So what we're saying is, if it takes 2 electron volts of energy just to get an electron off of a metal, well, we have to add a photon of at least 2 electron volts in order for an ejected electron to end up with any kinetic energy. Okay? And so these lines, or these graphs, I should say, look like this. Right? They're straight lines. Is that straight? That's pretty straight. Where here, well, that's our y-intercept. There's phi. Okay? Big deal, notice, this is the same form as y equals mx plus b. Right? Our b is really the negative of the work function. Notice that the slope, key elements to recognize, slope equals h, Planck's constant. Right? Y-intercept equals phi. X-intercept is something we call F naught, or the threshold frequency. Right? And that is the minimum frequency, well, I'll do it like this, frequency of a photon that will result in electron ejection. Right, and notice, well, at that threshold frequency, right, this is what we call F naught. What's the kinetic energy of the ejected electron? Well, it's 0, of course, right? There's some minimum energy. That's like saying, okay, we have a work function of 2 electron volts. Well, we had a photon with 2 electron volts of energy. Well, that's just enough to get an electron out of the metal, but not enough to give it any actual kinetic energy. Right, so it just sort of comes off the metal and sits there, as opposed to comes off and comes flying out of there with some big kinetic energy. Now, there's also corresponding to this threshold frequency, something that we can say, well, we can relate that to this, and lambda naught we call the cutoff wavelength. All right, so that's lambda corresponding to the threshold frequency. All right. Now I should say here, back to this threshold frequency thing. If we put in a photon at the threshold frequency, it will eject an electron, but it'll have with Ke equals 0. So that's a big deal. You put that in some problems, right? When you use this formula, and this is your new favorite formula, all right? Lots of questions will be about threshold frequency or threshold wavelength, okay? In those cases, you have to use kinetic energy, Ke max of the electrons equals 0. All right? Now, what is different? How could these graphs look different? Well, for all of them, the slope does have to be h, right? The slope is Planck's constant no matter what. But like we said before, here's what's different about each one. Different metals have different work functions, right? So here's a different metal, say, right? One different metal looks like this. One different metal, I'll extend this a little bit. A different metal, looks like this. They all have the same exact slope. They all have different threshold frequencies and cutoff wavelengths. Fair enough? Yeah. Okay. Let's solve a problem or two. Lithium, beryllium, and mercury have work functions of 2.3, 3.9, 4.5 EVs respectively. Determine the threshold. Okay, the threshold frequency for each substance. So for the first one, I'm going to do lithium only. It ends up being the only interesting one anyway. We have a work function of 2.30 EV. We want the threshold frequency. Well, I'm going to go with this. Whoops. Well, yeah. Ke max equals HF minus phi. It's the only equation we'll use with these photoelectric effect problems. And I should say also, sometimes, depending on what you're given, you could also turn that HF into HC over lambda. Right? No problem there. Same exact equation. Now, at the threshold frequency, right, at F naught, rewrite that a little, F naught, Ke max, is 0. So therefore, we get rid of that, and we say that HF naught equals phi. So F naught is phi divided by H. Now, here's the deal. Phi is in EVs, right? We know that H is 6.63 times 10 to the negative 34th joule seconds, right? I've started using a quantity for this instead of in joule seconds in EV seconds, right? So this is 1.6 times 10 to the negative 19th joules. And this goes with that. Oops, wrong one. Well, you get the idea. That stays, this goes. So that gives us, it's just more convenient here to use 4.14 times 10 to the negative 15th EV seconds, since our phi is in EVs. So that's 2.3 divided by 4.14 times 10 to the negative 15th EV seconds, right? Our EVs then cancel. We're left with frequency in per seconds, which is what we want. I grab my calculator here. Let's see. 2.3 divided by 4.14 feet, negative 1.5. And I get 5. Oh, hang on. Sorry. Wait for it. Yeah, and I get that F naught is 5.56 times 10 to the 14th hertz. Okay, so there's the cutoff frequency. Notice, again, we're always using for cutoff frequencies, we're using KE max of 0. That's what it means. Now, oh yeah, which of the metals exhibits the photoelectric effect? Well, what I would do for that is I would say, oh yeah, certainly we're saying if 400 nanometer light is incident. Well, what I'm going to do is look at what's the energy of a photon at that wavelength, right? There is an expression, same thing as saying E equals HF, there is an expression for energy of a photon. All right, and I'm going to do it again in EVs, so I'm going to use my quantity of H that I found down here. All right, so that's going to be 4.14 times 10 to the negative 15th EV seconds times 3 times 10 to the 8th meters per second divided by 400 times 10 to the negative 9th meters. E negative 1.5, 3 E 8, 400 E negative 9. Poop. Error. Ah, there it is. And I get here that the energy of this photon is 3.11, let's call it, EVs. Right? So we've just answered part B. Which metals exhibit the photoelectric effect with this 400 nanometer light? Well, the photon energy is 3.1 EVs. In this case, it takes 2.3 EVs to get the electron off of it. Well, we're adding 3.1, so yeah. For lithium, sure, check. We do exhibit the photoelectric effect, right? For beryllium, where the work function is 3.9 EVs, well, it takes 3.9 EVs of energy just to rip an electron off the metal. But we're only adding 3.1. That's not enough. Same thing for mercury. It takes 4.5 just to get an electron off. We're only adding 3.1. Not enough. So lithium's the only one that exhibits the photoelectric effect with 400 nanometer light. And if we want the maximum kinetic energy of the electron that's ejected from this lithium, well, we just do this. Ke max equals, well, how about this? What we're really saying is it's E photon minus 5. Okay? Same thing as us saying, you know, HF or HC over lambda. So, KE max, oh yeah, we said that this is our 3.11 EV that we shot in there, and it took 2.30 EV just to get one out of there, so that we're left with electrons with up to a maximum kinetic energy of 0.81 EVs. Okay? So there is, I forwarded you these 2 pages of notes. I've also, let's see, what else did I do for you? Oh yeah, there's also 3 more homework problems that I sent. All right, so those I expect you to have done tomorrow. And that'll be it. And that'll be all. Make sure I got everything set here. Yep, I think I did. Okay? Okay.